Hello. In this video, we'll introduce a problem where a decision maker is trying to make their decision under some uncertainty where the state of the world is unknown to this decision maker. And later we'll shortly introduce a concept called information structure or the signaling structure where this decision maker can receive some signals to help themselves to make a better decision, to get an ex ante expected payoff, which might be higher than before. Okay, so now before that we formally define this problem first. Okay, so as we mentioned, this is a decision problem under some uncertainty, so we use this omega to denote the state of the world. Okay, so omega from the capital omega, which is the state space. Okay, and this state, it cannot be observed by the decision maker, right? So this is the state, and there is an action from the action space, which is taken by this decision maker to try to maximize their own utility, right? So that's the decision that is going to be taken. So talking about the utility, so it's a map from the Cartesian product of the action space and the state space to a real number, okay? And it's simply a function of the a and omega, okay? And because the decision maker doesn't know any information on this state, right? So this decision maker has to hold some prior belief on this state, okay? So which is simply a probability over the possible value of this state, okay? So we use this mu to denote the prior belief, which is a map from the state space to a unit interval, okay, which is a probability. And this is the prior belief, okay? So as we mentioned, if this decision maker doesn't have any information to make the decision, then this problem is very trivial, right? So here we would like to introduce some information to this decision maker. So this kind of information that is delivered to this decision maker, this form is called the signal, or and it has their signal realizations, right? So a signal realization S from the space of the signal realizations. So this can be observed, right? So this is the signal realization and its space. Okay, so this is observable. Okay, and so that's the realization. So how about the signal itself? So it's defined by this pi. It's a map from the state space to the set of all distributions over the signal realizations. Okay, so this pi is the signal structure or the information structure that we mentioned in the beginning. Okay, signal structure or information structure, they are the same thing. Information, okay, structure, or we can call this as an experiment. Okay, so this signal structure is specifies a probability of sending some signal S given that the state is omega. Okay, or we can call this as the probability of receiving this signal. Okay, because now in this problem we do not have any sender yet, so, right? So we only focus on the perspective of the decision maker, who is just a receiver, right? So we don't need to care about who is sending the signal or what. Okay, that's something we'll talk about later. So the probability of receiving the signal S if the omega. Okay. So the decision maker wishes to make the inference on the state given those signals, right? And this decision maker, we assume that they are taking the actions, or they're forming their beliefs using the Bayes rule, or they're acting in a Bayesian manner. Okay, so the decision maker makes inference on the state, okay, on the omega given the signal, okay, and acts in a Bayesian manner. So we mean that they are updating their beliefs using the Bayes rule, right? Update the beliefs. Okay. So that's pretty much about this story. And of course, this decision maker has some strategy, right? So we use alpha, which is a map from the space of the signal realization to the set of all distributions over the actions. Okay. So this is a mixed strategy, and it specifies a probability of taking the action after observing the signal realization. Okay. So the expected utility for the decision maker from taking the alpha in an ex ante perspective, so then it's given by the following expression. So we have the prior and we have the signal, right? We multiply them together, then taking this action with the utility. Okay, so here, because we do not know the action or the signal or the state from the ex ante perspective, so we need to sum them up over actions, signals, and states, right? So suppose that alpha star is maximizing this expression, this expected utility. Okay, good. Now let's take a look at a very simple, brief example. Suppose that the state and action spaces are finite. So omega is simply containing two elements, omega 1 and omega 2. Okay, and the priors are the same for them, equals a half. And action space also contains two elements, a1 and a2. Okay, and the utility is very straightforward. If the decision maker successfully match the action number with the state number, then the utility is 1, otherwise it's 0. Okay, so in this case it's 1, otherwise u of a2 omega 1 or u of a1 omega 2 will be 0. So that's something easy to begin with. Okay, now we consider a signal structure or an information structure, and we don't need to care about concern that who is sending the signal. Okay, so that's some stories later, but now we just know that somebody just gave us this signal. Okay, so a signal pi, we say that the signal is such as if the state is omega 1, then this signal realization will be S1. The probability of being S1 will be 0.9. Okay. But if the omega is omega 1, then the signal is S2. This probability will be just 0.1, right? Because those two, they sum up to 1. And similarly, if omega is omega 2, and we let this probability of sending the signal S1 to be 0.3. So otherwise, it will be 0.7. Okay, so this is just an example. If we write them together in a little table here, so this is 0.9, 0.1, 0.3, and 0.7. Okay, so we mentioned that this decision maker knows some probability theories, so they're acting in a Bayesian manner to use the Bayes rule to update the prior beliefs to the posterior beliefs. So here we use the same notation, but here we are representing the posterior beliefs using the conditional probabilities, right? So this is omega mu of omega 1 given S1. So we simply use the Bayes rule to update the beliefs, and the numerator here is the prior times the signal, and over the denominator, which is the total probability of sending S1. Okay, so specifically pi S1, the overall probability of sending S1, this should be the summation of two different ways that this signal could be S1, right? So it can be the state is omega 1 or omega 2. So both ways can lead to signal 1, S1, right? So it can be mu omega 1 times pi S1 omega 1 plus mu omega 2 times pi S1 omega 2. Okay, so there are two different possibilities here, and they add up together to be the denominator. Okay, so what's the result? What's the number for this? So it's simply we plug in those numbers and we get the numerator is 0.5 times the pi here is 0.9 over 0.5 times 0.9 plus 0.5 times 0.3, right? And this is 3 over 4. And similarly, okay, we can calculate all those numbers, right? So we don't need to bother to write all those formulas again. So we here just write the numbers down. So mu omega 1 S2 will be 0.5 times 0.1 over 0.5 times 0.1 plus 0.5 times 0.7, which is 1/8. Okay, so similarly, mu omega 2 S1 is 0.5 times 0.3 over 0.5 times 0.3 plus 0.5 times 0.9, which is 1/4. And last, the posterior of omega 2 given S2 is 0.5 times 0.7 over 0.5 times 0.7 plus 0.5 times 0.1, which is 7/8. Okay, and we can notice that those two numbers, they add up to 1, and those add up to 1, right? So those are just the summation of the conditional probabilities, right? So this is very straightforward. Okay, so now we can go back and calculate our expected utility for the decision maker, right? So we write it again. Pi S omega alpha star A given S U A omega. Okay, so we sum over the actions and signal realizations and state. Okay, so here we notice that the alpha star, or the we say that the alpha that is maximizing the expected utility, given that the signal realization is S1 and the action is A1, then this should be 1, right? So this is intuitive because that given that the signal realization is S1, then the decision maker has no if this decision maker is rational, then they cannot choose A2, right? Because they will have a relatively higher probability that to know that the state is more likely to be omega 1, right? So because they're wishing to maximize their expected utility, given that the utility itself, the specification is to match the subscript of the state with the action, right? So similarly, A star of A2 and S2, this is one as well. And if A1 given S2, so this will be 0, right? This is alpha. Okay. Or the A2 S1, so those should be 0, right? Okay, so now we expand those terms. Okay, so we'll get 4 terms correspondingly. So those are mu omega 1 times pi S1 omega 1 u A1 omega 1, right? And plus the mu omega 2 times pi S1 omega 2 u A1 omega 2. Okay, so we simply expand those terms and to figure out that to write all the possible combinations of those probabilities, right? To get the expected utility. And plus mu omega 1 pi S2 omega 1, in this case, u A2 omega 1 plus mu omega 2 pi S2 omega 2 times u A2 omega 2. Okay, and we notice that those subscripts for the A and S, they should match, right? Otherwise, the terms will become 0. So we don't have those terms here. And we also notice that this term and this, they should be zeros, right? Because those two, they do not match. Okay. All right. So here we have the result here, which simply has only 2 terms left, right? Omega 1's prior times the signal of S1 given omega 1 times the utility of A1 omega 1 plus mu of omega 2 pi S2 omega 2 u A2 omega 2. Okay, good. So we plug in those numbers. This is 0.5 obviously, and this is 0.9 from the table, and this is 1 by the definition of the utility, n times 0.5 times 0.7 times 1. Okay, so the final result becomes 0.8, which is higher than a half, and we will shortly show that 1/2 is the expected utility, that there is no signal. Okay, so that's something we will see shortly. And intuitively, we can imagine this, right? So it's if there's nothing to tell the decision maker, then this decision maker has to take the guess half and half, right? And then by the utility function, then it's 0.5 as the expected utility if there's no information. Okay, so now we can draw this a little picture to help us understand what's going on here in this example. Okay, so the vertical axis is the utility for the decision maker, and the horizontal axis is the prior or the posterior beliefs. Okay. All right. So suppose that this is 1. Okay, and here's 1. So we have this little square, and this is 0. Suppose this is half. Okay. So we know that this line here, this diagonal, okay, is the expected utility of the decision maker from taking A1, right? The reason is that if the posterior belief is 0, then taking A1 leads to the utility of 0, right? Otherwise, if it's 1, then taking A1, it leads to utility, it yields a utility of 1, right? So we connect those two points and get this line of the expected utility for the taking the action A1, okay? So similarly, the opposite diagonal here, it is just the expected utility from taking action A2, okay? Good. So because this decision maker is a rational agent, and here if the posterior belief is less than a half, then for sure this agent is having something to, is taking some action to having a higher utility. So it means that this decision maker is taking A2 in this case. And otherwise, if the posterior is larger than a half, then this decision maker is trying to maximize the utility, expect utility by taking the action A1, right? So A1 in this case has a higher expected utility. Okay, so the green line here on this line are the actions, are the expected utilities from taking the corresponding actions, right, for the decision maker. Okay, so if there's no information at all, then we know that the posterior belief is the prior belief is 1/2. Then in this case, as we mentioned, so now we know that the utility, expected utility for the receiver, for the decision maker now is 1/2 itself. However, in this case, we have some signal or the information structure for this decision maker to consider, right, to update their belief. So in this case, what we can see from the picture is that this prior belief 1/2 is actually splitted, or it's redistributed to another distribution over the posterior beliefs, right? So it has a probability distribution over the posterior belief. So namely, we have already calculated the distribution or those probabilities. So here we can simply draw those points and the probabilities correspondingly on the picture. So suppose that this is a quarter, so here should be 1/8, right? So this decision maker, then after receiving the signals, then the decision maker knows that, or the decision maker updates the beliefs to believe something as follows. So there is a probability of 0.4 that we already calculated, right? So this 0.4 comes from here, right? So this is this plus this is 0.4, right? And this is actually this, right? So pi s1, this is 0.4, okay? And correspondingly pi s2 should be 0.6, right? That's something we can calculate from here, okay? Good. So with probability of 0.4, the decision maker has a posterior belief of 1/8, right? And with a probability of 0.6, this decision maker has a posterior belief of 3/4. Okay, so then we can see that this is very straightforward, that where the decision maker's prior belief is now splitted to those 2 points, right, with some probabilities 0.4 and 0.6. Okay, so now in this case, then we can find the expected utilities here and here correspondingly, right? So now we know that from the picture, we know that this decision maker is maximizing utility in expectation. So we connect those 2 points, okay? And using those probabilities, 0.6 and 0.4, to get the expected utilities, okay? And after we calculate that, we will find out that we have already done that, right? So it's 0.8 here. Okay, and later, shortly, we will verify that this point, it has the same horizontal axis with a half. Okay, so this point, the horizontal axis of this point, the number is exactly 1/2. Okay, so that's a very important property of the signaling structure here, and we'll shortly introduce that in later episodes, and that's something called the Bayes plausible, okay, in the information design problem. Okay, good. So we notice that this, if there's no information, then the decision maker has expected utility of 1/2. If there is some information, then the expected is 0.8. Okay, so this gap here, this gap of 0.3 is actually what we call the value of the signal, okay, the value of the pi. Okay, so that's a straightforward concept, right? So if we have the signal, then the decision maker could yield a higher expected payoff. So that brings some value from the signaling structure or the information structure, right? Okay, very good. So now we verify something we have mentioned here, and we calculate to verify what we just said. So as we mentioned, we have already calculated the overall probability of sending the signals say S1 or S2, right? So here we can explicitly do that again. Okay, we have already did it, right, from here. So this is pi S1, and we can write it again, and also for the pi S2. Okay, so pi S1 is simply the signal pi S1 given omega 1 times the prior of omega 1 plus pi S1 omega 2 of the times the prior of omega 2. And this 0.9 times 0.5 plus this is 0.3 times 0.5. And it's 0.6, right? So it's this number. And similarly, pi S2 is pi S2 given omega 1 times mu omega 1 plus pi S2 omega 2 times mu omega 2. Okay, so the important places are that here we wish to calculate the overall probability of signal 1. So here it must be S1. So here is S2, S2, so this is S2, okay? So this is something important to be noticed. And so this is simply 0.1 times 0.5 plus 0.7 times 0.5, right? So finally it's 0.4, okay? So that's this number. Okay, and now we can verify that something that we just said, that this point, it has a horizontal axis with the value of 1/2. So now let's see if this is correct or not. So we simply sum them up. We multiply pi S1 with the probability of the corresponding posterior, right? Omega 1 given S1 plus the overall probability of sending S2 times the posterior of omega 1 S2. Okay, so this is simply saying that what we are doing here is that we are calculating the expected value of the posteriors, right? Given their probabilities. Okay. So those pi's, they can be regarded actually as can be regarded as the probabilities of the posteriors, right? Okay, so that's something very important, and we will use that again and again later. So we calculate that, and we will find out that this is exactly 0.5. Okay, so that's equal to mu of omega 1. Okay, or mu of omega 2. So these are the same, but we're doing this for the omega 1. Okay. All right. So and we can calculate the expected utility from the picture, right? So it's simply that the expected utility is 0.6 times 3 over 4, right? So we have this probability of 0.6 times the height of this point, which is 3 over 4, plus 0.4 times this value, right? This probability times the height of this point, which is 7 over 8, and this is 0.8. And we have already obtained that value, right, from here when we did the calculations and expanded all those terms, right, in the ex ante expected utilities. And also it's the same as we just obtained from the picture, right, graphically. Okay, so the 0.8 minus 0.5 is 0.3, which is the value of the signal that we just mentioned. Okay, good. So here we can actually calculate this, right? So it's not hard to verify. We can do this very quick. So it is 0.6 times so this is actually 3 over 4, right? And plus 0.4 times 1 over 8. Okay, so this is 0.5, and it's the value of the prior of omega 1. Okay, good. So now we know that how this information structure or the signal structure can actually help the decision maker to make a better decision to possibly improve the expected utility, right, from this point to this point, right? By giving this information structure, the prior belief is distributed to those two different posteriors, right? So now there exists a distribution over the posterior beliefs. Okay, so this is the basic setup and a very straightforward example for that. But here there's only one receiver or one decision maker, right? So there's no information sender in this game. But in the Bayesian persuasion or the information design problem, they have in their game an information sender who can design this information structure. Of course, the sender will also have their own utility function, right? So the game will become more complicated and more interesting in that case. And here another thing to notice is that here we only have this one particular signal structure that is given by something else that we don't know, right? So perhaps we can consider that question is there an optimal signaling structure, or how would we compare those different signal structures or information structures, right? So how do we compare them, or what conditions can we use to compare or to establish any relationships between the experiments or between the signals?